Hello, everyone. Welcome to the Danley Sound Labs Fireside Chat. I'm Josh Millward, Product Specialist at Danley Sound Labs, and I'm your host for this series. Please be sure to keep your mic muted and camera off to help conserve bandwidth for those who are on slow connections. This week, Ivan Beaver is joining us. He'll be talking with us about spec sheets. What do the numbers really mean? After Ivan's presentation, we'll be taking questions and talking about them. Please use the chat feature at any time to send me your questions. I will ask the questions to Ivan when we get to that part of the presentation. Before we get started, I just want to take a minute to remind everyone that the Fireside Chat series happens every week with a different topic each week. Next week, Mike Hedden will be joining us for another exciting chat. Previous episodes of Fireside Chats are available on the Danley Sound Labs YouTube channel. We always try to get them up as quickly as possible, but please allow us a week to get it posted. With that, let's go ahead and get started here. Let me find Ivan in the list. And yeah, with that, why don't you go ahead and take it away, Ivan?
Hello, everybody. Thanks for joining us. Hopefully today we will be talking about spec sheets and what the numbers really mean. We'd like for them to tell us a lot more than they actually do, but we're limited to certain things. So let's get started. What do they really mean? Oops, hang on. Speakers work by being heard. There's nothing in the spec sheet that describes what a loudspeaker actually sounds like. Don Davis said years ago that you could have all the best sound measuring gear in the world, analyze a source, analyze a signal, but you have no idea what's actually being said. But a $1 speaker in a little plastic enclosure will let you understand what's being heard. So specs are great, measurements are great, but we still need to actually be able to know what it sounds like. If you take a piece of sheet metal and run it through a saw, you'll get really high SPL. Most people don't really want to listen to that unless you're into that particular type of metal music. And a toaster will handle lots of watts. If watts are the thing that really matters to you, plug a toaster into your amplifier. Not going to be very loud, but hey, it'll handle a lot of watts. Specs are generally just for comparing basic parameters, assuming that everything is being done in the same way, measured the same way, presented the same way. We'll see some examples of that as we go on today. The judge of quality is your ears. Different people like different sounds, and their perceptions are different. Some people like more highs or lows. Some people, they like it louder, they like it quieter. You can't please everybody, so you have to make up your own mind. But overall, the best thing is side-by-side demos. That's the best way to judge the quality of the sound. Your ears have a very short acoustic memory. It's hard to remember, well, what did that sound like last week? I really don't remember, so we highly encourage side-by-side demos when it gets down to the sound quality part of it. But there's other things that are important that we can get from spec sheets. We still need to have some numbers. That's where the spec sheets are going to come in. And the important thing is the numbers have all got to be tied together for them to make any sense. If they're not tied together, it can be random numbers that have no meaning whatsoever. And again, we'll see that here in a little bit. There's a lot of specs on the spec sheet. Some are pretty obvious. How much does it weigh? How big is it? That type of thing. And then some of them require a bit of understanding of what are they actually trying to say, or what are they limited by standards or this type of thing. We're not going to look at all of them, just some of the ones that seem to confuse people, be misleading, and hopefully get a little bit better understanding to what the true meaning are, how some of them, how they're achieved, and what to look out for when you're looking at specs. Smoothing is just one of them, and this goes on spec sheets, it goes into modeling, it goes on a lot of different parameters here. So here's if you were to look at just the response, which one of these loudspeakers would you like to purchase? There's loudspeaker A, B, or C. Which would, you know, if this is all the information you had, which would you go by? Well, the answer is any of them, because they're the exact same loudspeaker and it's all the exact same measurement. All I did is just change the way that they're displayed. It's the same data, it's the way the data is displayed, and you can get different numbers off of the data. So you got to look at and understand the numbers that are associated with that particular measurement. I'll go back here. The first one, this one is with a certain amount of smoothing. This one here, all I did is change the scale. It's the same exact measurement. I just changed the vertical scale on it to make it look smoother. And this one here is the actual unsmooth data with all the warts and all the ugliness, and so there's zero smoothing on it, but they're all the same thing. So which one of these has got the greatest high frequency extension? And this is the same, again, the same cabinet. If you look here, where does it roll off at? It depends on the amount of smoothing that was applied to it. Again, it's all the same data. So you need to know what you're looking at, because you can come up with some very different answers. So on that end. Okay, where to choose the numbers, and that's a topic of debate. And if you give one graph to a bunch of different engineers and say, hey, what are the numbers? And some of the numbers, hopefully they're gonna be in the same range, but they're gonna vary, because we're not dealing with flat line type stuff. What is the intended frequency range of interest? Not some out of band thing, like in particularly subs. This is where this gets to be a problem. So this is our BC 412, and we have a sensitivity that we rate at 112, as indicated by the red line there. Now, you could, if we wanted to, say, hey, well, we want to have a higher sensitivity, well, we'll call it 118, because there's a peak up there, and the cabinet will do 118 dB. There's no question about that. And that's still considered in the low range. It's still below 200 hertz, but not what we would consider the sub range. And it doesn't give a fair indication of what the overall loudness is, but it will produce that particular sensitivity at that particular frequency. So be careful on subs. Where does that sensitivity number come from? Is it in the useful band, or is it some peak somewhere out of band? Impedance. The impedance is not the DC resistance of the voice coil like that you would measure with a particular ohm meter. The DC resistance is always lower than the actual AC impedance, and the impedance is a combination of the DC resistance, the inductance, and the capacitance of the particular loudspeaker. And it's not a simple number. It can vary wildly with frequency. Typically, we call speakers 2, 4, 8, and 16 ohms, even though the actual load, it can be very, very different than that. And we made the mistake early on of having a speaker that was rated at 6 ohms, because that was an honest rating for the loudspeaker. And I got lots of phone calls that people couldn't find an amplifier that would drive it, because no amplifiers listed 6 ohms. So I changed the rating to 4 ohms, and the phone calls all stopped. So people, a lot of times, they just like to have simple numbers. They don't understand where they're coming from. And so we generally choose the closest standard number on the impedance. That's why we call it nominal. We also give you, on the spec sheets, we show you the minimum impedance, we show you the frequency that it's at, and we show you the impedance curve. So if you don't like my number that I chose, you can look at the graph and come up with whatever number you want to call it. And we'll see some more examples of that a little bit later on. We're not even going to talk about the phase of the impedance, because nobody puts that on a spec sheet, but that can be a lot bigger deal on an amplifier than just the actual ohm load. People get hung up on just the ohms, but what is the phase response of that impedance? Because if it's highly inductive or highly capacitive, such as a motor cabinet like the old servo drive cabinets, or capacitive like Piezo's, it can really overheat an amplifier and shut it down, even if the actual ohm load is relatively easy to drive. So ideally, the phase angle should be less than plus or minus 45 degrees. But again, we don't show it, nobody else does, but it's just another piece of information that there's more to what loads an amplifier down than just the actual ohmage of the impedance. Our TH115, the 4-ohm cabinet, is a good example of standard numbers. So here is the impedance of the TH115, and there's the 4-ohm line. And the standard rating, we call it a 4-ohm cabinet, but at no point does it ever go down to 4 ohms. 5 is the lowest that it ever gets, and if you want to look at an average, it's closer to 6 ohms or so. And at 51 hertz, which is right around the center of a lot of techno and EDM type stuff, its actual impedance is close to 22 ohms. So around there, it's not working very hard at all. So if your music is centered around there, the amplifier is going to love it. And some loudspeakers have dips below the rated impedance. It's usually not a problem for the amps, as this dip occurs over a limited frequency range, unless the dip is at the center of the frequency. Like if there was a big dip at 51 hertz and you're playing a lot of dance stuff, you're going to have a serious load going on the amplifiers that they may not like. This is our SH69. It's a 4-ohm rated cabinet, and there's the 4-ohm impedance line. And it does dip down a little bit below 4 ohms at a couple of frequencies, a little bit above 1K, and then up there around 14K. But over the majority of its operating range, it's well above 4 ohms. So the amplifier, unless you're doing sine waves at a little over 1,000 hertz, is not going to be a problem. Frequency response. Probably one of the most misunderstood and stretched specs. Often a single number is given, or a range of numbers, without any supporting documentation. And people want to assume that, hey, if it says it'll do 20 to 20K, by God, it'll do 20 to 20K. It may or may not. 3 dB and minus 3 dB, minus 10 dB. These are the frequency ranges in which the speaker is 3 dB or 10 dB down from something. The something is the big deal. It has to be tied to that, because a dB is just a relationship issue. And if it's, how do you know the relationship? I have half as much money as I had last week. Well, I don't know how much I have, because unless I know what I had last week, it's you have to have a starting point. And the sensitivity is what that something should be. The minus 3 dB must be tied together to the frequency response to have any meaning. If you want a higher sensitivity, then you got to be willing to accept a higher or lower frequency response number. And if you want a higher or lower frequency response number, then you got to accept a lower sensitivity on the spec sheet. And that's why we show you the spec sheets, the actual frequency response, the raw response, unprocessed, so that you can see what's going on and see where all these numbers that are in the simple numbers, where they come from. So let's use the BC415 as an example. If we wanted the really high sensitivity, the 118, then the real minus 3 dB points would be 112 to 139 hertz. As you can see, I just popped up there on the graph. This is the frequency range. This minus plus or minus 3 dB, or the minus 3 dB points. So who's going to buy a sub that goes from 112 to 139 hertz? Hey, but it will get pretty loud, and if loudness is all that you're concerned about, then it'll get loud at some frequency, but it may not be at the frequencies that you want it to get loud enough. What you want to know is how loud will it get at 50 hertz, at 60 hertz, of frequencies that you're interested in, or in some cases 20 hertz. And it's important to compare the simple numbers to the measured response. Now, this is an extreme example of this is an actual product, not ours, and I've removed all names and model numbers, and I will not disclose them, so don't ask. But it's a good example, and I have a little collection of a lot of wild stuff. It's like, where the heck did they get these numbers from? And this is just one of the more extreme examples here. So here we go. This is the manufacturer's data. And this is really not part of this discussion, but I wanted to add it. you'll see that there's actually two curves here. There's the deep and the punch mode. Well, there's a number of manufacturers, and they have they call them deep, they call it the base mode, they call it the infra mode, but it doesn't actually add any low frequency. The low frequency, when you put it in that mode, it doesn't go any lower. All it is it just lowers the low pass, so you have less highs. And you can do a quick, easy test to yourself. Take a sub, it doesn't matter, and do a low pass at 1,000 hertz and play some music. It's going to sound like there's no bass in it at all. Now just take that low pass and swing it down. By the time you get down to around 100 or 80 hertz, something like that, now you're going to be able to hear the bass. Did you increase the bass any? No. All you did is get rid of the highs. So be careful. Just be aware that all they're doing is just getting rid of the interference, but they're not actually adding any more low frequency there. But anyway, that's not the point of this discussion. So just kind of look at that graph. It'll come up again here as we go on. It's a powered loudspeaker, so there's no sensitivities given, but let's assume that it's 100 dB. So we'll go back up to here, and 100 dB is around the range of in the bass range, even though it's a limited bass range, but that's what I'm calling it 100 dB. That's where I would call it. So, and they say that the minus 3 dB point is 30 hertz to 120. Well, if you actually look at the graph, down at 30 hertz, that's actually 27 dB down from 100 dB, not 3 dB down, and 120 hertz is 18 dB down, not 3 dB down. So if you think that the 30 hertz is going to be loud out of this cabinet, well, 27 dB down is not exactly very loud. So if you assume the 100 dB sensitivity and real 3 dB response ratings, you'll end up with a response from around 44 hertz to 82 hertz. So this is about the range that the cabinet should be spec'd at least as far as I'm concerned. So how many people would buy a sub if it was rated from 44 to 82 hertz? You know, that would be quote known as your one note subs. So sensitivity. Sensitivity is a rated SPL sound pressure level when a specific level, voltage, not power or watts, is applied to the loudspeaker. This is only good for non-active loudspeakers. And opinions differ on what the applied signal is. A lot of people use 1 watt. It's the common term. It's very misleading because you do not apply wattage to a loudspeaker. You apply a voltage. The wattage that's being dissipated is the result of the applied voltage and the impedance at a particular frequency. The impedance is going to vary quite a bit with regards to frequency, so the same voltage at different frequency will produce different wattages. So if you were to actually do a 1 watt, apply 1 watt to it, and the loudspeaker was root or flat, it would look like the impedance curve, and nobody would buy it because, wow, that's a terrible response. So you don't apply wattage, you apply voltage. So for a constant 8 ohm load, let's say a resistive 8 ohm load, when you apply 2.83 volts, you get 1 watt. But if the applied signal is watts, you know, in other words, they say 1 watt, you don't know what the actual applied voltage is. Do not assume that it's 2.83 volts unless they say so, because it could be a higher voltage. Like, for example, in the we showed earlier, the TH115, that was minimum was 5 ohms, but probably ought to be called 6. If we did the voltage for a 4 ohm load to be 1 watt, we're going to have a lower sensitivity. But if we actually use the higher impedance that it is and applied 1 watt to that, we'll have a higher sensitivity. So it can be very misleading as far as the wattage, and I think that's something the industry needs to get rid of, but it's ingrained in people, and somehow, and that's just what they get stuck with. So just be aware that the wattage can end up with different numbers because you don't know what the 1 watt actually means. We only use 2.83 volts, no matter what the rated or the actual impedance is. This way you can easily compare the loudness of different models with the same drive voltage. At lower impedance, it'll result in more than 1 watt being dissipated, but you can figure it out. For 4 ohms, you subtract 3 dB, 6 dB for 2 ohms. from the standard 8-ohm number, but at least you know what the drive signal is, and that stays constant. Since the response of the loudspeaker varies with frequency, it produces a different SPL at different frequencies with the same input. So the rated sensitivities should be some sort of an average SPL within the intended operating band, as in draw a line around the average of the dips and peaks within the intended operating range. As we saw earlier on, like the BC 412. Sometimes with sub and bass cabinets, a higher frequencies is used to get the higher sensitivity, and it's out of band. It gives an unrealistic idea of what the loudspeaker is capable of. Remember the example we showed earlier with the sensitivity that was out of the intended pass band. Sometimes it's across the peaks in the response, sometimes getting a higher number than the average number that you would actually want to see out in the real world. And here is that response there again. There was one manufacturer years ago that had a double 18 with a really high sensitivity number, and it had a peak up in like 1800 hertz. I don't know about y'all, but I don't normally run my double 18s up to 1800 hertz. And it was true that loudspeaker did have that sensitivity in a 20 to 20 kilohertz range, but it was very unusable, and it didn't tell anything about what it could actually do in the bass range, but it would get that loud. So they weren't lying, but they weren't telling you the truth like you think that you ought to be told or what you were expecting. So there's that peak that if we wanted to, we could call it. And on the subs, we do list these peaks for people that want to play the numbers with loud stuff. I mean, with other, the loudest point to just compare, but we tell you what it is, we show you what it is. So there's nothing being hid there. Make sure you know where all the simple numbers come from. Don't just take, hey, here's a frequency response and here's a loudness. If they're not tied together, they're completely meaningless. Maximum SPL. It should be pretty simple. How loud can it get? Well, there's a lot of variables, and they should be easily measured, but it's not as easy as you would think. The max SPL is usually stated as an unweighted peak SPL. Most people, unless they've got a more advanced sound meter, they've got a simple SPL meter, and they don't have an unweighted response, and they don't have a response time that can measure the short peaks. The maximum number, they have a max hold on a lot of standard meters, is not a peak from a standpoint, but rather the highest value that the slower than the peak responses show. And so here's a way that you can actually take your SPL meter and test it, see if it can measure peak capability. Just snap your fingers about 2 feet away. A good finger snap, you should get 105 to 110 dB. If you're getting something a lot lower, your meter is not capturing those peaks. A good hand clap is about 125 to 130 dB. Some people's are louder, but you go, wow, a hand clap is 130 dB. Yeah, if you measure it properly. So you need to don't trust that your meter is a peak reading meter. If it's not, then you're truly not reading the peak SPL. Max SPL doesn't say anything about the sound quality of that loudness. It just means that it will modulate the air and produce that sound pressure. Doesn't mean that it sounds good. It can sound like garbage, but as long as it's doing that SPL, it's meeting the spec. So when we're playing music, the reading on a normal SPL meter with an A weighting and fast response, even though A should never be used above anything above like 60 or 70 dB, but it's become standard these days, but we won't go down that road. But it's an average about 15 dB or so lower than the peak or the maximum SPL on the spec sheet. The loudspeaker is producing those peaks, but your meter is not able to read it. So we get called all the time. Well, I can't, your speaker says it'll do 130 dB, but I'm only reading, 115 or 120. Well, yeah, it is doing the 130, but you don't have a meter that can read it. And with some shows, an unweighted peak can easily be 30 dB or higher than an A slow response. Sometimes you'll see continuous and peak max SPLs. This is a calculated number using pink noise with a 6 dB crest factor as a stimulus, and then using the sensitivity and the power handling as the starting numbers, and then they calculate it. There's various versions, and we do the same thing. There's various versions of pink noise that are often used. Obviously, the flat one, but very often the IEC or AES is used. It's normal peak noise, but it's got the high frequency and the low frequency rolled off to better simulate the amplitude of what would be considered music, and that's what's determined by the standards committee. Now, what's considered music, different styles are going to have a different response, so it's a general overall average, and it closely resembles the response of music, but not the crest factor. So recently, M Noise that Meyer Sound Labs is I'm not sure if they developed it or they've adopted it. I think they've adopted it from somebody else, but I won't go down there. It's starting to be used by some manufacturers. It's a noise source that is replicable and closer resembles music on both the crest factor and it also, the crest factor varies by frequency, and then the frequency response has the overall curve on it, kind of similar to the old AES curves. And it will give a peak value that's actually much higher, 17 dB, than the continuous measurements. And this is an actual measured SPL, not calculated, so you actually measure the loudspeaker, and it's based upon the power compression point of the loudspeaker or the limiter in active loudspeakers, which is minus 2 dB from a lower level. So you crank the level up until you get 2 dB into power compression or 2 dB into limiting. You measure it, whatever those numbers are, there you go. That's how loud it goes. And we're working on providing both the calculated, the sensitivity and the power capacity, just like we've always done, numbers, and the M Noise SPL figures. This will make it easier to compare simple loudness to other loudspeakers. As a side note, I'll add that of the ones that we started doing, we've actually been measuring, in some cases, peaks that are 10 and 12 dB higher than our calculated numbers. Not all of them are that high, but they've all been on the peaks, have been exceeding our calculated numbers. So you can take our calculated numbers as being conservative, but we are going to start adding those to the spec sheets in due time. So just pay attention to that. It'll be coming as we get it done. One thing that you can check the calculated numbers is to do a little bit of math. And this is it's real easy for passive speakers. Biamped and triamped, that gets to be a little bit harder here. But you figure out the gain capability of the loudspeaker. This is done by knowing the rated power capacity in watts and the sensitivity rating, and then you just add them together. So if you've got a loudspeaker that's rated for 1,000 watts continuous, it'd be 4,000 watts peak, which is a 6 dB crest factor. Whoop, hang on. There we go. So the dB gain is the math is 10 log 1,000 over 1, 1,000 being your watts, and then 1 watt you're assuming, and we're going to go just because we are dealing in watts in here, we're going to stick with watts, but you could convert the watts to voltage and do the same math. You'll have the same answer. You end up with 30 dB, and that's just a number that needs to be ingrained in your mind. 30 dB is 1,000 watts. The easy way to remember it is it's 10 dB for every zero. So you got 3 zeros in 1,000, that's 30. 100 would be 20 dB. So that ought to be ingrained in your simple basic knowledge. And so if the sensitivity is 100 dB, you have 100 plus 30, you have 130 dB continuous, and you add a 6 dB for crest factor, and you get 136 dB. So that should be by looking at the wattage capability, that should give you the maximum SPL, so you can double check to see, hey, are these numbers adding up? It's good to double check. So let's go back to the speaker we were using earlier, the powered speaker. Okay, so it's 30 hertz to 120. It has a max SPL of 136 dB, and the amplifier has got the 2,500 watts peak. So 2,500 watts, that's the maximum the amplifier is going to do. So that gives us something to work on. So you take the 2500 or 10 log 2500 over 1 is 34 dB. So the amplifier has got 34 dB. It's got 136 dB rated capacity minus the 34 dB gain. That would leave 102 dB sensitivity for the loudspeaker. But that doesn't add up when we look at that loudspeaker response we had earlier. At 102 dB, that's right up there at the peak of the response, not in the average. So over just a couple of hertz, it'll do 120 dB. I mean 102 dB. Everywhere else, it's going to be lower. So since that's at the peak and not the 100, guess what that also does? That screws up the frequency responses. If you accept the 102, then the actual 3 dB that's 30 hertz is now 29 dB down, and so the real minus 3 dB numbers should be 48 to 71 hertz, not 30 to 120. And it's a good way just to double check different parts. Does everything add up? If it doesn't, then something's going on somewhere. Wattage capacity. You have to assume that the wattage given is accurate. It's a bit involved to test that, and you don't want to be blowing stuff up. And we're not talking consumer watts. We're going to assume that that professional manufacturers are giving you real accurate wattage numbers. But a minimum test of that should be the rating of the driver inside the cabinet. Like, let's say a sub has got a 1,000-watt driver in it, then the cabinet should be rated 1,000 watts, not 2,000 or 3,000. Or in the case of a multi-way cabinet, a 2 or 3-way cabinet, add up all the wattages in the cabinet. But that doesn't always apply because it depends on the horn loading and the crossovers design. Sometimes the multi-way cabinets, the wattage can actually be higher than the sum of the individual drivers. And that really is a cabinet-to-cabinet thing. But you can get in the ballpark anyway. It's also important to understand what this rating means and how it's achieved. It is a very specific signal with a defined crest factor and frequency response applied for a specific period of time. Excuse me. It's not indefinite. As soon as you change anything, time, crest factor, or the frequency response, the power capacity is also going to change. It can go up or down depending on what you end up changing. Music's very dynamic and doesn't always fit into these standards. And so the standard wattage is a guideline for an average type of use. And it gives you an idea of where to set the limiters. You calculate on the voltages based on the impedance and just basic math there. And gives you an idea of where to start based on those wattages. And it gives you an idea of the size of the amplifier to use. It's generally recommended to use something between the continuous and the program rating of the loudspeaker, which is a 3 dB difference. The difference between the continuous and peak is 6 dB. We normally don't recommend running amplifiers up at at the peak capability because so many people will just take it up to there using that as not for peaks but a continuous and just drive the average level too high and it's bye-bye loudspeaker. If you know you're going to be driving the loudspeaker really hard for like extended periods of time, you're out in the desert and you're doing a 24-hour, or in some places in Europe where they'll run from Friday afternoon till Monday morning, back when you could actually go to clubs and do that. There's going to be a lot of heat that's going to be built up over that time period. It's not the time period for the power rating, and so you need to set your limiters lower to account for that. So don't assume that well, I set it for this and I ran it and I never stopped. Well, yeah, you also killed it because you were doing something that the spec didn't say that the loudspeaker could do. And setting limiters is a whole different discussion. We'll probably be doing one of those here coming up in the next couple of weeks or so. Coverage pattern. It really is a completely involved separate discussion, but we'll touch on a few little things here. Suffice it to say that the rated pattern rarely covers the entire operating frequency range. The size of the horn or the spacing of the drivers, if they're used for cancellation, makes a huge difference, as well as the actual rated pattern. Suffice it to say that a large horn is a very good thing. In most cases, the rated pattern is only good for the top couple of octaves because you have little bitty horns. You have to look at the polar patterns or the balloons coverage to see exactly what's going on, of what the actual particular pattern is at a particular frequency. And in most cases, it's very, very different than what the specs say. So the idea of a small rotatable horn and being able to control the pattern is nothing more than marketing wishes or installers' hopes of, hey, I got a 6-inch two-way speaker and it's got a rotatable horn, so I can keep the energy off of the walls there. Yeah, right. So here's the math that you can do, that you can do your own calculations with. So this is the Don Keel's formula for the minus 6 dB points. For those in the States, it's 1 million divided by the size of the horn in inches times the rated pattern. For those over in the rest of the world, it's 25,400,000 times the size of the exit in millimeters times the rated pattern in degrees. So and if that's on the Danley ruler, which may be another topic that we do, a standard formula, but that's a good formula to know, just to have an idea of how big does this horn actually control down to. And once you do the math, you'll quickly realize how little the little horn controls. If you got a 6-inch horn that's about 40 degrees, it's going to only control from 4,200 hertz up. So you got the top 2 octaves. As you go lower and lower, it gets wider and wider. So it takes physical size to actually be able to control stuff, not a number on a spec sheet. And a lot of people they often miss is the importance of the pattern degree. The narrower the pattern, the larger the horn has got to be to have the same control frequency. Or conversely, a small horn that's got a wide pattern can actually control lower. And so it doesn't have to always be big. The pattern of the horn in degrees is just as important as the physical size. And always remember to question the simple numbers on the spec sheet. Look at the graphs for the real answers. Don't just take the numbers as they're spitted out to you, because you don't know where they came from. There's no basis for that. And as one of my favorite sayings, a complicated question is easily answered by a simple, easy to understand wrong answer. So we deal with a lot of things that are very specific, and they have different answers, depends on how you look at them. So look at the numbers, understand where they're coming from, look at how they're related. Or does it make sense, or do they seem to be related? We can mathematically compare them. Let's do this. Let's see how things are all added up. So anyway, that's the end of my presentation here, and I guess we'll open it up to questions. And Josh, you want to take it over from here, or?
Yeah, we can do that. Thank you, Ivan, for that. I'll switch back over here. We've had some really good questions show up here and comments show up in the chat box. So we'll go through some of that stuff. The best question is from Abe. He said, "There's a Danley ruler." To which, yes, Abe, there is. Kyle responded that, "Yep, Abe, you got to go to Infocom to get the good swag, pal." Which unfortunately, since we're not doing this year, makes it a little tough. But yeah. I think we will probably do something with that. I've got one of the audio rulers right here in front of me, and it's covered with all kinds of really great formulas and reminders and points. Probably one of my most favorite things on this ruler is Ivan, where you put in there the lengths of the distance of the wavelengths of various frequencies. I think that's a really handy thing to have on here, because it reminds you of how big the wavelengths are at different frequencies. And it's only a 12-inch ruler, so it only goes down to about 1.2K. But I think it's a really great method to remind everyone what the wide variety of distances that we have to deal with are, and how getting things within that quarter wavelength to get them to couple, especially at higher frequencies, is extraordinarily difficult.
Yeah, and one of the things about audio that makes it so hard as compared to other, shall we say, engineering disciplines, is that size of the wavelengths. We deal with a ratio of 1,000 to 1, 20 hertz to 20,000 hertz. Okay, lighting, well, visible lighting deals with a ratio of less than 2 to 1. You know, or go to an RF engineer and say, hey, I need you to make me an antenna that will cover, you know, a range of frequencies from 1,000 to 1, and they're going to laugh at you. No, the antennas are tuned for very narrow frequency ranges, and we deal with an extremely wide frequency range, and that's what makes so much in our industry so hard, is because it is a very, what applies at one end doesn't apply at all at the other end of the spectrum, while everybody else is pretty much the same thing.
Right. Yeah. It's definitely a unique thing for our industry. So one of the first questions that we'd gotten here is from Rocky. He's wants to talk about watts a little bit, and I agree that I'll add a personal comment here first. I have issue with with rating everything in watts. Loudspeakers are rated in watts, amplifiers are rated in watts. Problem is that watts is not something that you directly measure. Watts is an answer. Watts is the result. It describes how much work is being done. You know, what you're actually doing, as Ivan said earlier, you're applying voltage across a load and passing so much current through it, and that it's that relationship which results in watts. So Rocky's question here is, so your loudspeaker ratings, continuous and peak, are rated in watts. Would you consider supplying specs with V-Peak, V-RMS, etc.? How do I correlate your power ratings with voltages for setting limiters when I don't have a DNA amp? Does continuous watts rating correlate to V-RMS?
Yes, and there is no such thing as RMS watts. There is voltage RMS, but there's no such thing as watts RMS. So hats off to getting the terms right on that. And as far as the simple way, if you take our continuous ratings, the continuous wattage rating, and then you figure out what the voltage is based on the impedance, okay, then that would give you what I would call the one possible limiter setting. The problem is there's different when you start talking about limiters, and I don't want to go off on that, but do we have one limiter? Do we have three limiters? Do we have other ones? What, you know, and then it comes down to like styles of music, because if I'm doing jazz, I'm going to set my limiters differently than if I'm doing, say, a dance club with the same loudspeaker. Okay, and if I've only got one limiter, if I've got multiple limiters available, like the DNA amps do, and other amps do also, then you can use the different ones, different limiters set at different points, depends on what you're doing. And if you have to choose a simple single number, I would do the continuous rating, converted that to volts, and then the attack time would be at whatever your high pass filter's at on that cabinet. So you know, if you're it'd be 1 millisecond if you got it set at 1,000 hertz, 10 milliseconds if it's set at 100 hertz, 20 milliseconds if you're at 50 hertz, that type of thing. So I would set the that's my, you know, I have different answers for different things, depends on what tools you have available, and that's why limiters are a whole nother discussion that I think we're just going to redo one of my talks that I did at InfoComm a couple of years ago, and so will give us a some more information on that, and when you have different types of limiters and different things on that. Hopefully that's not too confusing, maybe.
Right. perhaps should we go ahead and give them the actual formula for calculating the attack in milliseconds? The answer is milliseconds, and I believe the frequency is 1130 divided by the high pass frequency.
No, that would be for the size of the wavelength. Okay, so
okay, all right.
Okay, it's 1,000. Basically, 1,000 hertz is 1 millisecond, and that's something that's one of these standard numbers that everybody, if you're in audio, you ought to be able to spit that out, and everything's multipled. So 100 hertz is 1/10 of 1,000, so it's 10 times that. So 100 hertz is 10 milliseconds. 20 hertz is, 50 hertz is twice 100 hertz, so that's twice 10, so it's 20 milliseconds.
20 milliseconds.
So,
right. Okay.
Yeah. So that's the and so, but if you think of 1,000 hertz as being 1 millisecond, 10,000 hertz is 1/10 of a millisecond. And,
right.
And these are just you ought to be able to, not pulling out a calculator, just off the top of your head, just go real quick, just being able to figure that out,
Right. Yeah, you should be able to rough it in really fairly
close
quickly.
enough. We're not going to argue, is it, oh, well, it's set at 90 hertz, so should I set it at 10 milliseconds or 11? I don't care. It doesn't matter.
yeah, close enough. Close enough.
And the other part of the math, if you want to go and figure out, well, so what is the voltage? If you just take whatever the power rate, the continuous power rating, multiply that times the impedance, and just use the rated impedance on this, and then take the square root of that. So the square root of the power times the resistance, or the impedance, will give you the voltage that you set for the limiters.
Right. That's basically the using the regular Ohm's law calculations, right?
It's Ohm's law. Simple Ohm's law there. And if you're wanting to do some peak stuff, and then a continuous thermal long term, those have different formulas. So, but for the simple one is power times voltage, and take the square root of that. There you go. That'll get you doing 90% of your work.
Right, and I think those voltages are the same, are the numbers that we put on the DSP settings worksheets that we distribute. So Rocky, if you've gotten any of those that have the EQ settings that we use in our DNA amplifiers and the high pass and low pass filters and that kind of stuff, the voltages that are listed on there will be calculated in this fashion.
Yeah, and the and if you don't have that, Josh can get that to you. That's not a problem.
Yeah, just reach out to me and I can help out with that. Related to this, so Abe then asks, wouldn't providing V-Peak and V-RMS make it easier for people to set up limiters if they aren't using DNA amps? And yes, that's exactly what we're talking about.
Right, and part of the thing comes down to how much information how many lines have we got on a spec sheet? We start throwing in all of this different type of stuff, then it starts being a little bit confusing. So part of it is we leave some stuff off like that just because it makes for a little bit cleaner spec sheet. And so it would be a good idea. But we don't want to end up with we could do the polar plots and a lot of this stuff rather than looking at the looking at it in direct and this sort of thing. It's a matter of how much information goes on the spec sheet, and so that's the reason why we don't put that on there. But I will agree, it would be a good idea. So maybe in the future.
Yeah, so Rocky further asked also, why are the recommended power ratings twice the continuous?
Well, because music is not a sine wave. Okay, if we were dealing with light bulbs, your light bulb has a sine wave going into it. The wattage is real simple, you know, unless things vary from the power company. It's real simple. Music is very dynamic, and and typically music is going to have about a 15 dB crest factor. So you're not normally going to be running pink noise into your system for an extended period of time. So it's just, that's just been, and again, that's a general rule, but it's open to debate. As far as how big of an amp do you want to go, and then it also goes into the operation. How responsible is the operator? Are they going to take that headroom and just slam it to the wall, or are they going to just barely let it tickle it? You know, and it depends on what the operators are going to have different ways that they do things. And so what, to me, it's, and I've been in this situation when I was doing the rental stuff. Oh man, just turn it up a little bit more. Yeah, just so you know, it's like, listen, we're at the limit of the system. Oh man, yeah, but if it blows up, man, we'll pay for it. We'll pay for it. Okay, great. So here it is. It's 2 o'clock on Sunday morning, and the speaker system blows up. You having a party now, or did everybody go home? Okay, and you're the only one complaining about it being 3 dB louder. How about we just leave it where it's at and everybody enjoy themselves, you know? And so it's just to try to keep the loudspeakers working for another day is way more important than it being a little bit louder, you know, to make 1 or 2 people happy, you know. And that's my opinion.
Yeah, that's about the time that I turn it down 3 dB and say,
yeah,
there you
exactly.
go.
Yep, exactly. You want it louder? We'll go down again.
So Matt mentioned here that that measuring that voltage at the amplifier output needs to be done with a true RMS meter, which is a good point, because yes, your typical low-cost multimeters or DMMs and things like that are typically they're typically tuned more for 50 to 60 hertz because that's power range. You need something, you know, that's more functional over a wider range if you're trying to measure, you know, 1K or something like that at what the actual output is. And also, then Rocky mentions, but the amp ratings are based on crest factor signals, not continuous sine signals, which is very true. And therein lies the conundrum of, you know, do you want to look at the crest factor maximum outputs of the amplifiers, or what it's actually continuously capable of, because they're sometimes substantially different things.
And I would add, if you're measuring the output of the amplifier, do not have the loudspeaker hooked up to the amplifier. If you do,
yeah,
you're asking for trouble. You're asking for a blown loudspeaker, you know, and the amplifier, in the case of modern amplifiers, will not produce that full output. Okay, because they are a burst type amplifier. However, the modern class D amps will produce the full continuous voltage when there's no load. So disconnect the loudspeaker, put a sine wave in, and run it up, set your voltage there. Everything's good to go.
Right. So Kyle here had posted a question. Can you explain why you think the calculated and M noise peaks are so disparate on some boxes? From what I've seen on most Meyer boxes, for example, the M noise comes out lower than calculated by about 1 to 3 dB. Is it perhaps because they use 12 dB or more crest factor? And are you guys using 6 dB crest factor? I've seen crest factors of up to 16 dB used for some manufacturers.
Yeah, and the M noise has a crest factor of 17, or I think it's maybe even 17.2 if you want to get particular, I think. But the one of the things that we are going to go back, and we have typically, Danley has typically been very conservative in our wattage specifications. And one thing that we're going to look at going is to go revisit some of the specs and and come up with some more accurate stuff, and we may just leave things where they are. But now I will say that in the M noise measurements on a couple of products, the continuous has been like 1 or 2 dB down. I think maybe the most was 3. But part of that is M noise is looking for -2 dB deviation in response, while standard power handling is looking for -3. And it's also very frequency dependent. So it depends on where the deviation was starting to take place, and in the Meyer instructions on how to use it, if I'm not mistaken, they look for something that's deviation of at least an octave wide, and I don't go for an octave wide. I go for anything that drops down to 2 dB. So we're being even more conservative on that. So some of our numbers have been conservative to begin with. That's how come we're ending up with higher numbers on the with the M noise. And again, that's something that I started on it a while back, and I've been away from it for a little while. I'm going to get started back on it again, but but it's trying to, I applaud them for what they're doing, trying to give something realistic that is a repeatable and a measured, because if you look at some of the examples that we had, we can calculate all kinds of different numbers. Doesn't mean the loudspeaker's actually going to do it. So with the excuse me, with the M noise, it is a actual measured response. You have to have a peak reading meter, and this sort of thing, which we have plenty of. But it's a step in the right direction anyway. How many people are going to adopt it? I don't know. I do like, and one thing on the last line of the instructions that Meyer has is that, so go test your loudspeaker here, and then contact your loudspeaker manufacturer that they need to change their spec sheets to match the new ratings with the M noise. And when I read that, I chuckled to myself and I said, "Oh, you mean we get to make them louder?" they were insinuating that you need to make them quieter because it's actually measured versus the calculated. In our case, we can raise the numbers. So but we're still going to do it the same way. We're going to do the calculated, the simple calculations that we've been doing, and then we're going to be doing the measurements also. So and then there's another test that we may end up doing, and it ends up with a bunch of different numbers because it's a number per frequency, but it's looking for acceptable distortion, and that's going to be per frequency. So it'll be different levels at different frequencies, and it's based on the harmonic distortion of the loudspeaker. And that's a real interesting test that can come up with some really interesting numbers. And that would be something that's closer to getting what does it sound like, because at least it's taking into account distortion. Normal SPL numbers do not take into account distortion. You can have a lot of distortion and you're hearing mostly distortion, but it's still producing that SPL, while this limits the distortion, but it's only good up to 1 kilohertz. So, but that is something that we're looking at doing, just as a way of trying to, hey, here's some more numbers of some realistic stuff that's actually, and this is measured, this is not calculated. So, so that's just another thing that we're looking at doing, trying to give more information.
Right. So going back to what you were talking about earlier with the sensitivity ratings on our spec sheets, well, on everybody's spec sheets, Rocky was pointing out here that you might want to add to that the sensitivity rating differences, well, the sensitivity can be different, or is different, depending on whether you're measuring in full space, half space, or I believe he says I believe Meyer still uses quarter space.
I don't know. I've never seen anything from Meyer that says quarter space. They do with the M noise stuff. They say half space, which that's the way that we are measuring the loudspeakers, because that's what goes in with quote their instructions. The way that we do loudspeakers on subwoofers, they're all in half space because they're sitting on the ground. Even if you fly them, you as a person is going to be in a half space environment. So therefore, it's still going to be a half space environment. On our full range speakers, we get them up in the air so we don't have the boundary loading, and so the frequency response doesn't go as low and they don't get quite as loud, but it is more representative of the SPLs that you're going to get when you actually fly something. Now, the exception is like the monitor speakers, the LPM, the SM80M. Those are intended on sitting on the floor. So those are actually measured in a half space environment, even though they are a full range speaker. All the other full range speakers are actually up in the air. The mic's up in the air, the speaker's up in the air, and so they're in a whole space environment. So yeah, that does vary depending on the type of loudspeaker. We already state that in the spec sheets of how it's actually measured. So
right. So Kyle mentions that if anyone wants to see the balloons, directivity, sensitivity, or frequency response plots for competing speakers or the Danley ones, then AFMG's GLL Viewer software is free, and most manufacturers provide GLL files for their boxes on their websites. Whether that data is heavily smoothed or cheated a bit is another matter, but directivity is usually visible.
Yeah, and that's totally true. I've been in a number of cases to where I've been on site with a particular product, and the consultant saying, well, I can prove to you in ease that it does this, and our answer is, yeah, but I'm standing in a room and I'm telling you it ain't doing it. And I will say there is fudging that's going on. And that's just and there's a lot of little tricks that you can do in ease, even with the same data. That depends on how big you make your plots, all sorts of little things that you can smooth things and make it look nicer or worse, even though it's the same particular thing. So there is a lot of fudging, I'll say fudging, that goes on, and that's just the way it is. But at least, if you try to make some of the numbers like what I went through and make the numbers add up and back calculate, make them see if they agree, at least that gives you an idea on those numbers if they're fudging or not. But hopefully on the directivity, and it depends on how many data points they've got, and I know that and I'm not picking on Meyer, but I'm just going to use this because this is where it comes from, that, well, everything should be measured in 1 degree increments. Well, first of all, that is a whole heck of a lot of measurements when you start doing a full balloon. And my opinion is, if you need 1 degree increments to describe the character of a loudspeaker, you got a really messed up loudspeaker. Because if it's gonna, if the difference, if I'm 1 degree off axis or 4 degrees off axis, if it's different, that's not good. So, but then you can go to really wide increments and going, well, that really doesn't describe it either. So there's arguments of both ways, and of how much data is there. But from the balloons and stuff, yeah, that would be a good thing to look at. And it's important to look at balloons, see how things are actually behaving. And it's trust me, loudspeakers are far from perfect. I mean, I wish ours would be the perfect patterns that we say. They're not, but they're very good over most of the range. And there's a few anomalies here and there, and that's just life. But you'd be surprised at looking at some other manufacturers how huge the anomalies are. And it's like, well, how do they get this number? That number is not even remotely close to what it does. But somebody decided to be a good marketing number, and so they stuck it on there. Because at some frequency, it will be 90 degrees or 40 degrees at some frequency. What it is at everything else doesn't matter. So.
Right. Well, and the same thing goes for, the max output from these boxes, from a lot of boxes. Every self-powered 12-inch two-way these days can do 131 dB, right?
Yeah. Yeah.
As an example of that,
that's another story.
Yeah, well, exactly. As an example of that, Scott had sent me a message here where he reminded me of the demo that we had done against a very popular 12-inch two-way self-powered cabinet that's rated for 131 dB peak in a small club. They had a pair of them, and for the demo, Scott brought in a pair of go-tos. What was it? 2 go-tos and 1 TH118XL we hauled into this place, and a DNA 20K to run them. And and quite frankly, the two go-tos smoked the pants off of that self-powered 12-inch two-way box. You know, where the heck they come up with and how the heck they think they can justify rating it to 131 dB is kind of crazy, but they do. You know, those
Well,
numbers are on the spec sheets, and it's probably, you know, one of those when lightning strikes kind of numbers,
yeah.
because, you know, it may not work after it does 131 dB, but it still did it. So guess what? That's the number we're putting down.
Well, there is one manufacturer that has a high output, a very well respected manufacturer, high output floor wedge that's rated at like 141, 142 dB. And if you actually look at their specs and go through their data, like in ease, you'll see that where that comes from, that's at 1.2 kilohertz. And it's where that 2-inch driver gets really stinking loud. Now, higher or lower that in frequency, the level is closer to 130, 131 or so. And so while it's true that speaker can do 142 dB, it's only at 1.2 kilohertz. And typically, I don't want to hear 1.2K at 142 dB, you know, but the rest of the speaker can't do it. So they're, again, it's one of these things, they're not lying. The speaker will get that loud at some frequency, but can it do it at all frequencies? That's the important thing.
Is it useful? That's the question. Is it usable?
That SPL, exactly. Yeah. And so the example that I give, I tell people all the time, I've got a 300 horsepower car. I get 100 miles a gallon, and I can prove it to you anytime. It's easy to get 100 miles a gallon. All I got to do is go to the local mountain up here, put it in neutral, and just coast down the mountain. I'll get at least 100 miles a gallon. Now,
or more.
Or more. Yeah, but what people want to know is, well, what am I going to get driving around town? I didn't say it was driving around town. I said I could prove to you that my car could get 100 miles a gallon, and it will, but in an unusual, stupid circumstance. So that's where you have to be with these numbers, that it's like, yeah, it's a completely unusable number, but I'm not lying because I just proved it to you. So it gets to be really strange sometimes.
Yeah, Abe mentioned he's getting 2 weeks to the gallon on his car at the moment.
Yeah, exactly.
So,
exactly.
so if anyone has any more questions about what we've talked about here, go ahead and plug them on in so we can chat with Ivan about it. Otherwise, we'll be wrapping things up here in a minute.
Oh, and by the way, just for those of you that are out there, I hope you were paying attention, because coming up here in the near future, that we're going to be doing an audio 101 test and things that everybody ought to know, and we covered a lot of those concepts today. So pay attention.
Yeah, we're going to have a test later, and we're going to go over a bunch of this stuff, and hopefully, well, let's see. I don't think they're going to need. Are they going to need a pencil and paper to be doing figuring on that test, Ivan? Or
it's a test that I did about 10 years ago. It's just, I don't know why I did it, but was that I considered basic audio 101 knowledge. That if you went to audio school, this should be the end of the first semester. You should know this stuff. You're not going to need a calculator. You're not going to need a pencil or piece of paper. This should be stuff you ought to be able to spit off the top of your head. And it has to do with relationships like wavelength, power, blah, blah, blah. And the idea is we'll give the question, we'll give some possible answers. You choose your own answers. We're not keeping score. It's for you to test yourself. and then we'll go through and discuss the question about where the answers are, what you should know about the question, and that sort of thing. So I think it's going to be a lot of fun. So
yes, I'm looking forward to that. Absolutely. There will be a lot of good discussion around that, I think.
Yeah.
So
Not and
Ian,
this is 100% no manufacturer specific. This is audio. I don't care if you're doing consumer audio, car audio, metal or dance stuff. It doesn't matter. It doesn't matter what loudspeakers. All of this applies to every audio out there.
So Matt just asked, can we get a copy of the test? And John said he needs a study guide. I think, Ivan, had you once posted some of these questions on ProSound Web?
I don't think so. I don't
No?
think so.
Okay.
No, I don't think I posted it. I've just handed it out to a few people here and there. I don't think I posted anything. So.
Okay. All right. So there is no test out there that you can look at. He handed it out.
It's to test yourself. Do I know the answer to this? Whoa, maybe I need to learn a little bit. That's what it's about. It's more about of a it's not trying to make a fool of anybody, and so nobody's going to give any answers. So don't be afraid. I'm not going to show up for that one. I don't know if I can pass it. No, this is for you to test yourself and hopefully have some fun, and then also hopefully learn something.
So basically, it is fundamental audio stuff.
Yeah.
Is what it is.
Yeah.
I know I'm getting some messages here from lots of folks who are wanting to know, like, what's this quiz going to be over? And it's like, well, it's fundamental audio stuff. You know, when I read through it, Ivan handed it to me. I looked at it and I started laughing when I looked at it, because I was like, yeah, this is all basic stuff that that anyone who considers themselves a professional in the audio business should be able to pass, even if they have to stop for a minute and think about it. A lot of it is common sense. If you understand the basics of things like Ohm's law and how audio works, you'll have no problem with it.
But it should be fun. So
yeah,
I'm looking forward.
I think it'll be a great time. The Kim just mentioned that there is a self-test on SynAudCon's website. So if you want to brush up on some basics, that probably wouldn't be a bad idea. I know SynAudCon does has a lot of online courses available these days. So,
and it's a great resource. I'll say it is not inexpensive, but it is going to be money that that's very, very well spent. I support SynAudCon totally. So if you can afford it, go take some of their online stuff, or better yet, I don't know if they're even doing the in-person stuff now. But it's I've been to like 21 of them, and it's been very well worth it. So
yeah, Kim mentions here that the self-test is free, so no worries about having to spend money to take the self-test. You can at least take that part for free, and get up to speed on some things.
Or find out what you don't know, what you don't think you know.
Right. So anyhow, if that's it for the questions, then I guess that pretty much wraps up this week's Fireside Chat. Thank you, Ivan, for joining us this week. It's a pleasure as always to have you here and sharing your knowledge with everyone. I know we all definitely appreciate it. And I want to thank all of our attendees for coming. I see that we still have quite a number hanging on here. So thank you guys for coming. And next week, be sure to come back again at 11 a.m. Eastern, same bat time, same bat channel. And we'll have Mike Hedden here to talk with us again about some more fun stuff. So thank you, everyone. Have yourself an awesome week. Well, rest of the week. Tomorrow's Friday already, and then we're in the weekend. And have a great week next week. So we'll talk with you later.
Y'all take care. Bye.